so let's get started. First of all, are there any questions about the homework? Yes. Okay, so what do I want from the output for the programs? Okay, the program here is supposed to be just a simple test of prove that you can you know how to work adjacency lists well enough to find connected components. That is what I am asking you to do. Is this right? Is this consistent with what everybody thinks? Yes?
Well, what I meant was you want to have a written graph, you want to print out a table.
Okay, so what do I want you to do? Okay, I want you to give me a representation of what the connected components are. The easiest way is to list out their names. Okay, list out the names of the vertices in each component. Okay, that would be the easiest thing to do. Yes?
Do you want the code as well?
Yeah, so what I want to see is, okay, I want you to print out of the code, okay? And again, recognize that, the homeworks are not a large percentage of things. We want to just check to make sure that you've got your program there, okay? So that's my concern. I don't care about the format. I don't care about the language, okay? I just want you to be convinced that you know enough how the connected components algorithm works, that you can make it work. Okay? Again, the logical ways to print out the components are, for each component, list the vertices, or perhaps for each vertex, list the number of what component it's in. Yes?
So it's okay if we give you the source code in the form of a Piet picture.
In the form of a what?
A Piet picture.
Piet picture. What's a Piet picture?
It's an esoteric programming language or the source.
Okay, you give me whatever language you want, okay, so long as we can recognize it as a program, okay? If you give me a sheet and you tell me it's printed in an invisible format, and I won't accept that. But other than that, the vision is just to see that you know how to do it. That's what I ultimately care about. Any questions here? Any other questions about homeworks or logistics or anything like that? Yes?
Yeah.
Okay, what was the question?
Did anybody misread the homework and not do 413, 414?
Okay, so several people will complain. Okay, so let's just think what you're saying. You think you're complaining about the last homework that we just passed back.
Yeah.
And you're complaining that a bunch of you seem to have misread something. Is there a logical explanation for why you misread it? Yeah.
Everyone says this number and this number, this number and this number, each of the 1 through 5, and one of them says this number to this number.
Okay.
I think a lot of us miss that.
Okay, so that's a good thing for me to try to do on tests, I guess, right? No. Okay, so the answer seems to be, okay, so let me think what I feel about that. Send me a mail to remind me this. Send me a hostile mail. I promise I won't do it to any class in the future. What I will do for you guys is unclear, okay? So, because I did have these things. If you feel really strongly about it, here's what I'll say. Turn in on your next homework, turn in those missing problems, okay? That much I'll say. And write a big note on it saying, I was violated on the last one because of this. And I will direct the TAs for it. That's a fair way to deal with it, okay? Any questions about that? Okay? Okay, fair enough. Let's now get through any other questions before we get into this. Yes?
For question 512, it tells us the square directed graph is, it says give efficient algorithms both adjacency lists and matrices.
Yes.
Understand are we supposed to construct?
Okay, so this is a problem that is asking you to construct something called the square of a graph, which means, given a graph, construct a graph where you have an edge between every path of length exactly 2. 2 vertices if there's a path of exactly 2 between them. Okay, that's what the problem is asking, correct? Now, you can imagine one algorithm on sparse graphs, which would be good to use an adjacency list. And you can imagine one algorithm that is good on dense graphs, in which case you're dealing with an adjacency matrix. It turns out the matrix algorithm here is kind of interesting. I'll give you a little hint, because the reason they call it a square of a graph is it's sort of, kind of related to squaring a matrix. You know, multiplying a matrix by itself. Okay, maybe that, and so that's why I ask you to do the graph algorithm for sparse graphs and for the dense graphs. And so I guess I'm asking you for two algorithms. One good for sparse graphs, which would be using adjacency lists. One would be good for dense graphs. Yes.
So the output of the algorithm should be like if there's edges x, y, z, then any g squared, we should show how to add xz to a new graph.
So it says that I'm given as input a graph G, I'm outputting a graph H. If there is a path from X to Y and Y to Z, in G, there's going to be an edge from X to Z in H. Okay? Any questions about that? Okay, any other questions here? Okay, so let's just say, while we're talking about it, I want us to finish up with shortest path. I want us to finish with graph algorithms today. The problem of the day, if I am correct, is something we've sort of already answered in here, but it's kind of an important thing before we go and do our shortest path thing. I guess it's 615, which says that if there is you have a graph and you have a shortest path spanning tree rooted in a vertex of it. Now if we add edge weights to a constant to every edge weight in the graph, is this tree still the shortest path spanning tree? So there are a couple of questions here. What do we mean by shortest path spanning tree? And what's going on? Here is, again, we'll go through this example a couple of times. This is, and unfortunately the pen is still dead. So let's see if we can do this here. Let's write fair. Okay, this would be another long day. Let's try, you want me to say pen. Here is a vertex in the graph. If we look at what is the shortest path from our start vertex to every other vertex, that is going to define a tree. Let's think about this for a second, okay? It should be clear that every vertex there is a shortest path to every vertex in the graph. There might be multiple ones, but there is a shortest path to it. If we take the union of those shortest paths, that's kind of what we mean by a shortest path spanning tree. Although it shouldn't be obvious that that actually is a tree. Maybe we'll go to the board here just to talk this through. Suppose, let's say, we have a graph. Here we've got a graph. Let's make a graph that looks like this. I'm just going to make a look at it. And I'm not going to show you okay. What I claim is that for every weighted graph, okay, and any starting vertex, there is a tree representing the shortest path to every other vertex, okay? Now this may not be immediately obvious, okay, but what are we saying? It should be clear that every vertex, there is a shortest path from V to every vertex. That much should be clear, right? We could imagine taking a graph, building a subgraph of the graph, consisting just of the edges that were in the shortest path between that vertex and every other vertex. Is it obvious? Okay, let's say that's not obvious yet. Okay? Let me see if I can come up with a good example on the fly. Okay? Let's say that this was 2, 1, 3. Okay? And I haven't decided what I want to make the other one be. What is the shortest path from S to every other vertex? Okay? I claim the shortest path to this vertex, okay, is of weight 2, The shortest path to this vertex, let's make this 1. Okay, let's make this 1. Okay? So everybody see that this is a shortest path here to this vertex. Does everybody see that? Let's say that this was let's give this one an edge of 4. What is the shortest path to let me just look at this for a second. What is the shortest path from here to this vertex? How long? Yeah?
I'm going to perversely suggest it's 1, 1, and 3 rather than 2 and
Okay, the important thing to see here is of weight 5. Does everybody see that? What else does one see about this? That there are multiple ways of getting there at cost of 5, right? You can get there this way, you can get there this way, you can get there this way, right? Now, this I claim is let me add this thing. This here is a shortest path spanning tree. What do I mean by a shortest path spanning tree? Given the starting point, it defines the way for the shortest path to every other vertex. Does everybody see that? The shortest path to get to this vertex is that way. The shortest path to get to this vertex is that way. Does everybody see this? This is a tree, okay, and it encodes the shortest way to get between here and every place else in the graph. Does everybody see that? Any questions about that? Now, it should be obvious that for every vertex, starting from any vertex, there is at least one shortest path to every other vertex in the graph, right? Everybody see that? Now, it should be clear if we union all of those edges, we pick a shortest path to every other vertex, okay? We can union those edges, and those edges will be enough to find shortest paths from our source to every other vertex. But it's not obvious that that union of edges has to be a tree. In particular, there is an equally short path from here to there, right? And if we take the union of 3 of these paths, the shortest path from here, ka-chunk, 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 the shortest path from here, ka-chunk, and the shortest path from here to ka-chunk, does everybody see that that's not a tree? Okay? So it should be obvious that we could find the shortest path from our source to everybody else. We could union them to get a short representation of the shortest paths, a concise representation. It is not obvious that has to be a tree. Any questions? But I claim there is going to be a tree with that property, okay? And it has to do with the consequences of how we find shortest paths, the so-called Dijkstra's algorithm. And maybe before I go to answer the problem today, let's go into what Dijkstra's algorithm is again. Okay? It has a tremendous amount to do with Prim's algorithm, but it's also, just like the others, kind of amazing that it works. What is Dijkstra's algorithm going to do? It is going to start from a particular source vertex, let's call it this one, and it is always going to find what is the next vertex we can claim that we absolutely, positively know the shortest path to that vertex. Okay? And the way that it's going to do it is just like Prim's algorithm. It's going to take what we know about vertices in our shortest path spanning tree so far. Right now, our starting point is the only vertex in it. What vertex here do we absolutely, positively know the shortest path from A to? Okay? From looking at this. Yeah? The one directly up, 5. Now, why do we absolutely, positively know that there is no shorter path between A and this vertex than that path? Yeah?
The other 2 paths are already longer than that path.
You're saying because this path, the vertex going through here has to have a path of at least 7, and any path going through here has to have a path of at least 12, and so that has to be bigger than that. Yeah?
What if there was a negative?
What if there was a negative edge in there? How do we solve this problem? We say there can't be negative weight edges. You want a negative weight edge, you find yourself another algorithm. Is that clear? Okay, you got to be assertive with these graphs. Okay? And this is why not having a negative weight edge is a critical thing here, right? At this point, just looking at the local turf that we see right around A, we know there can't be a cheaper path to this vertex than 5, because we know there aren't any negative weight vertex edges in the graph. Okay? Any questions about that? Now, we know that this is the shortest path. We've now added one vertex to what's going to be our shortest path spanning tree, knowing that it has to be the shortest path to it. Now, which is the next edge that we're going to add? Okay, let's think about it. We can get to this vertex at a cost of 7. We can get it to this vertex at a cost of 12. How much does it cost to get to this vertex? Okay? Yeah?
7 or 4, but I guess something else.
Not 7 or 4. How much does it cost to get to this vertex from A? Okay, yeah?
12.
12. Why is that? It's because it cost 5 in a shortest path distance. It cost this total of 5 to get to here plus 7 to get to there. Right? Does everybody see that? This is the sole difference here between Prim's algorithm and Dijkstra's algorithm, is that the cost of adding this edge in a minimum spanning tree to join this vertex would have cost us 7 in a minimum spanning tree. But the distance to this vertex is going to be 12 now. Does everybody see that? Yes?
So it doesn't matter if there's an 11 path, you have to take that 5 first?
Does it matter that there's an 11 path? Okay? Well, it does mean that if I added this to my minimum, if I added this edge to my minimum, if Dijkstra's algorithm added this edge to the shortest path spanning tree, it would be wrong, is what you're saying. Because you're saying, look, there's a way to get to that vertex at a cost of 11. Dijkstra's algorithm is going to find the shortest path from A to every other vertex in the graph, right? It had better not pick this edge next, right? Does that answer your question?
Yeah.
What should it pick? What vertex not in the tree do we absolutely positively know the shortest path to it? Okay? I claim it's got to be this 7 over here. Does everybody agree? There is no way to get to this vertex less than 7, because why? That is the fringe vertex that it is cheapest to get to, okay? Given the state of the tree, okay? Any questions about that? Now, which is the next vertex that is cheapest to get to? Okay? Yeah?
3.
Well, 3. I could get here at a cost of 10, right? Because that's 3 plus 7. I could get here at a cost of 11. I could get here at a cost of 11. What is the next vertex that I absolutely positively know the shortest path to? It is this one. Does everybody agree with that? Okay. Now, what vertex do I absolutely positively know? I can get to here at a cost of 12, because that's 10 plus, does everybody see why it's 10 plus 2? Okay. I can get to here, I have a way of getting there at a cost of 11. By adding this, I got a new way of getting there at a cost of 12, but that's not that exciting. I have a new way of getting here at a cost of 17, but that's not so good because I can get to here at a cost of 11. I claim I can either get here at a cost of 11 or there at a cost of 11. And without loss of generality, I'm going to pick, just because I feel like it, this one. And now I know the cost of getting here. Any questions about that? That doesn't introduce any new vertex or any new vertex that's within one hop of me, right? Now which vertex? I can get here at a cost of 10 plus 2, or I can get here at a cost of 10 plus 12. The important thing is here I can get here at a cost of 7 plus 4, or I can get here at 7 plus 5. The cheapest way to do it is this, okay? And once I've got this, what are my choices? I can get to this vertex at a cost of 11 plus 5, or 16, or this at a cost of 2 plus 10. This is the right thing to add. Okay? Any questions about that? Do you see that we are doing almost exactly what Prims is doing? Okay? We are in each round adding a new vertex to a tree. The big difference is that the criteria we're going to add the next edge such that we add the next vertex such that the total cost of getting to that vertex is minimized. And the cost of getting to that vertex is the cost of an edge plus the cost of getting to that other vertex. Okay? Before it was just the cost of the edge. That was the only difference. Okay? And what's great about this is this gives us a shortest path tree. We get the shortest path from vertex A to every other vertex in the graph. Okay? Any questions about that? So it wasn't obvious that this shortest path structure could have been encoded as a tree before. You just take the shortest paths and union them. You've got lots of equivalent paths. It's not clear it works out right. The result of Dijkstra's algorithm is a tree that tells us the shortest way to get from our starting point to every other vertex in the graph. Any questions about that? Okay. Any questions about correctness? Okay, why is this correct? My argument is, at every point we are adding another vertex to the collection of things we absolutely positively know the shortest path to it. There cannot be negative weight edges in the graph because we forbid it. If every other vertex we can prove there is no faster way of getting to it, then this is going to be the next vertex to add. Okay? Any questions? And just like we did over here, adding this vertex might lead us to find the shorter path to a vertex that we already had a tentative possible way to get to. Okay? But we don't add it to the tree unless we can prove that there is absolutely no possible shorter path to it. Any questions about that? Yes?
So whenever you do ties, you just do whichever.
Whenever we do a tie, we are saying we know that there is no shorter way to get there. We might as well add one of them, right? It doesn't really matter. We can break ties arbitrarily. Okay? Presumably the next thing we're going to do after we add this one is add the other end on the tie. Okay? Any questions here? Okay? So if you look at what, any questions about how you do Dijkstra's algorithm? Okay? The thing that isn't here, that you have to see here is, well, let's just look at the program. Again, let's look at the idea now. Come. And we'll just talk about it one more time just to make sure this is completely clear. Okay? The idea behind Dijkstra's algorithm is basically the following observation. Okay? That if we have a shortest path, let's say we want to find the shortest path from S to T, and it happens to pass through some vertex X, we had darn well better have the shortest path from S to X. Okay? If we are going to find the total shortest path from S to T. Okay? So what Dijkstra's algorithm is doing is one by one finding the provably shortest path from our start to another vertex in each round. Okay? And using that to build up, so in each round we can provably find the shortest path to another vertex. Okay? And eventually we will find the shortest path to the one that we care about. Okay? Any questions about the philosophy here? Or the ideas of this here? Okay? Fair enough. Okay? So what is the basic data structures here? Let's just make sure of it. Again, we're going to keep track of the distance to each vertex. Okay? And originally the distance from our start vertex to itself is 0. Okay? If all edge weights are positive, the smallest edge incident to a vertex is the shortest distance from S to that vertex. Then what we're going to do is every time that we add another vertex to our shortest path spanning tree, we're going to go through its outer edges and see if there is a better way to get from S to some other vertex through this new guy. Okay? And in that sense, it's just like Prim's algorithm. Any questions? Kabunk. Okay, again, I've talked about it. It's the same thing as Prim's algorithm. Again, I showed you last time how much it was like Prim's algorithm. Okay? Everything is going to be the same in my implementation, except the name of the algorithm and the one critical criteria here. Okay? What is this doing? We are now going to, again, Prim's algorithm, if we go back to it before, it maintained which vertices were in the tree before. It was a Boolean thing. It maintained a distance matrix array such that distance of I was going to be the cheapest way of adding I to the tree that we know about. Okay? In Prim's algorithm, that meant the shortest edge between a vertex out in the tree to our vertex. Okay? Now distance is going to be really distance. It's going to be the distance from the root source vertex to one endpoint of that edge that's joining us, plus that edge. Okay? So again, the critical thing here is before we were going to be asking ourselves, okay, what's this basically going to be doing? We have a vertex V, okay, that we just added to the tree. We're going to go through all outgoing edges of V, okay? Let's say there is going to be a vertex that's going to go from an edge that goes from V to W. If the distance we know of to W is bigger than the distance to V, plus the weight of the edge from V to W, that means we have discovered a cheaper way to get to vertex W through vertex V. Does everybody see that? And that is why we're then going to say, well, the new way of getting the distance to W is that cost, and the way of actually getting to W is through V. Okay? This is all exactly like Prim's algorithm. In fact, if you want me to now turn it back into Prim's algorithm, what do I need to do? All I need to do, maybe I'll even do it in a black color to make it more like it's Prim's algorithm. All I would want to do is I am going to be asking, this will turn it back into Prim's algorithm. The cost of adding a vertex is no longer going to depend upon how far we are on the tree, only the cost of the last edge. If we change these two things, then we are back to Prim's algorithm. Any questions about that? How many people get this? See why it works? Okay? Any questions? Like a question like, I don't see why it works. Okay, is a good question. Any questions? Okay? So basically that is Dijkstra's algorithm. That gives us a way to find the shortest path 3, okay, between a vertex and everything else. Okay? Any questions? Now let's go to the problem of the day. The problem of the day asked us, if I am correct, okay, suppose we are given an unweighted graph, okay, a weighted graph, and we have a shortest path spanning tree rooted in V. Now we increase all the edge weights by a constant amount. is that tree necessarily still the minimum, the shortest path spanning tree? Yes, who says yes? Who says no? Okay, more no's, so that's probably right. Okay? What is the example here? Let's take a look at it. Can anybody give me a graph where a simple graph G, where here's my start vertex, and when I add a fixed amount to it, it's going to change the shortest path spanning tree? Can anybody give me such a graph? Yes?
Make a triangle.
Make a triangle. Ka-chunk, ka-chunk, ka-chunk. And what about this triangle?
Edges 1, 1, and 3.
Okay, does everybody see? Here we have a graph. What is the shortest path to get to this vertex? It is of length 1, and it goes through that. Does everybody see that? If, if we, the shortest path to this vertex is going to be 2, it's going to go through this. Does everybody see that? Is there something we can add to every vertex to change the shortest path spanning tree, the topology of it, yeah?
We can add 2.
If we add 2, suddenly this becomes 3, this becomes 3, this becomes 5, and now the shortest path spanning tree is going to be what? Okay? It is now going to be the 1 hop distance to it. Okay? Any questions about that? Does everybody see this? Okay. So the shortest path spanning tree is interesting. It encodes what the shortest path is from one vertex to all the other vertices. Okay? Any questions? So in other words, if you want to find the shortest path from here to California, let's say, okay? And you use Dijkstra's algorithm, you may say, I only want the shortest path from here to California. Note that Dijkstra's algorithm is basically going to give you the shortest path to every other place in the United States in order to do that. Okay? Any questions about that? It's actually kind of interesting that there is no algorithm that is known that is faster to find the shortest path between a given pair of vertices than to find the given a vertex and all the other ones, at least in the big O worst case sense. Okay? Any questions about that? Okay, so the shortest path spanning tree is a nice thing and a good thing. Okay? Any questions about it? And does everybody see that the topology changes, okay, when you add weights to things in ways that didn't happen for minimum spanning tree? Any questions? Okay. What is the cost of finding the minimum spanning tree? The Dijkstra's algorithm. It should be clear that the running time of this is going to be the same thing as prims. The only thing we changed, we didn't really change anything except this constant time operation right up here, right? What did we do? For every outgoing edge from, we exploring a vertex V, from every one of the potentially n outgoing edges, we are seeing if, from the new vertex that we have added to our tree, we are seeing, does this give us a better way to get to some other vertex? If distance of V records the cost of getting to every other vertex, then we can take a look for every outgoing edge from V. It's going to go to some other vertex. The cost of getting there is the cost of getting to V plus this edge. If this leads to a shorter way to it, update it. This is going to take order n time. Then to find the smallest vertex, okay, the vertex that is not in the tree, okay, that is the shortest distance away, we have to scan through all n of these things in that distance matrix to find the smallest one. This is n, we're doing it n times. The cost of finding Dijkstra's algorithm with this implementation is order n squared. Any questions about that? Okay? Any questions? Now, would n squared be good enough for your GPS device. Okay, let's think about this. If you went to Google, you went to your GPS, and you say, GPS, find me the shortest path from here to a particular taco stand in California. Okay? That is going to be how many different, let's say, destinations are there? Okay? If you think of an n-squared algorithm in a map of the size of, which has basically every house and every address. Okay? How many houses and addresses are there in the United States? Someone want to estimate, yeah?
Too many.
Too many? But how many in this case? Okay, I would guess. What am I going to guess? The average person has one address where they're at. They call their own. Okay? So that tells me it's about 300 million or so. Maybe it's 100 million. Maybe it's a billion. Okay? But if you did 100 million squared, that is going to be hopeless. And there's no way Google's going to give you a computation like that for free just so they can show you an ad. Does everybody see that? So you need a faster algorithm, okay, in practice for finding shortest paths on really large graphs. And the amazing thing is that, in fact, Dijkstra's algorithm will sort of do that, okay? There is a version of Dijkstra's algorithm that will run faster on sparse graphs. Remember, what's a sparse graph? A sparse graph is one where the number of edges is linear in the number of vertices, okay, roughly, okay? And that would certainly be the case with road networks, okay? So we can kind of imagine the United States probably looks like you've got 100 million vertices, okay? And you've got 100 million edges, 200 million edges, something like that. Big, but not unbelievably big. There is an M log n algorithm, okay, version of Dijkstra's algorithm, okay, which is better on, which for a sparse graph is going to be better than n log n, than n squared. For a dense graph, n could be as big as n squared log n is bad, right? But for a sparse graph, this is going to be more like n times log n, which is a reasonable computation even for pretty big values of n. What is the key idea to doing this in n times m time? If it's a sparse graph, let's look at our code here. What are we doing? Okay? Over at this part of our computation, we are going through, for every vertex that we add, we are going through all the outgoing edges from that V. The time this is going to take is not order n, but order what? Okay? Ordered proportional to the degree of each vertex. If we think about the road network, what's the degree at any given place? How many roads can you go to at any junction or city? It is presumably a constant. Okay? Certainly, this is going to go around according to the degree of the vertex. And in fact, the total amount of work that this part of the code is going to do over the entire execution is the sum of the degrees, which is basically order m. It's twice m, because every edge you're going to look at going once and going the other way. So the total amount of stuff here is going to be order m. What is going to happen here, though? Okay? Actually, it's sort of order m plus the cost of maintaining, it's basically order m, because whenever we update something, here we're just changing an array value, right? Updating the distance there. Here our basic job is to find what is the smallest value in that distance array. And if we have an array, and it's an unsorted array, an unordered array, to sweep through it to find the minimum is order n. How might we do a better job? Is there any data structure, though, that might be better for repeatedly finding what the minimum is in something? Okay, we have a set of numbers, yeah? A heap, that's why God created heaps, right? Was because we were repeatedly doing what? We were repeatedly wanting to find the smallest element in our heap and deleting it, right? Which vertex is closest to me, right? So how much is going to happen for every deletion? It's going to take, if there's n things in my heap, it's going to take log n time to update it, right? Now, how many times are we going to go to the heap here? Let's think about it. Here we have n iterations, each of which is going to ask which is the smallest one. That would seem like it is n times log n. Does everybody see that? Okay, any questions? Note, however, that when we come over here in this part of the code, if we're going to be storing the distance to a vertex, where distance is now going to be a heap, every time we find a shorter path to a vertex, that means that we've got to change that value of the vertex. Does everybody see that? So vertices, the values of something are going to change, okay, potentially during the course of execution of this. And the number of times it might change is every time we see an edge, we might change the distance to a vertex. And how do we change it? Well, we have to take that element, delete it from the heap, and then reinsert it with its new value. And so bottom line is, if you understand this reasoning, that sort of is all you really need to do in order to prove a bound like this, okay? Where for every edge operation we might have to adjust our heap. Every time through, once we have our heap of vertices, because we may change the distance to it. And then in each one of our n iterations, we're going to pull the top off the heap, okay? Bottom line, this is an m log m implementation and much better for sparse graphs. Any questions about this? How many people see why the heap is kind of doing the right thing here? Okay, any questions? Any questions about the bookkeeping or anything like that? And I can tell you there's even more macho data structures that will do better than this. Okay, so the actual real way of engineering, exactly what Google does to engineer their shortest path algorithm. So they will give you these shortest paths for free. They put a lot of engineering into that. Okay, and there's several tricks that are involved with that. But bottom line, at the heart of it is presumably a Dijkstra-like algorithm. Any questions about that? Okay. Any questions about finding shortest paths or how Dijkstra's algorithm worked? Okay. Any questions? Like I say, Dijkstra's algorithm is worth knowing because it's just shortest paths occur everywhere. Okay, and learning to look out for them is an important thing. Any questions? Okay. So Dijkstra's algorithm is a great algorithm for finding the shortest path from a vertex to any other vertex. Okay? But, so what's good about Dijkstra's algorithm is once I have found the shortest path from here to every other place in the universe, if you want to drive from here to Chicago, I know the shortest path, right? If I want to drive from here to Poughkeepsie, I know the shortest path. Does, however, the shortest path spanning tree help me find the shortest path from Chicago to Poughkeepsie? Okay, do you see kind of what my problem is? I have figured out from my shortest path algorithm the shortest path from me to every other vertex in the graph. Does everybody see that? That's basically what my shortest path spanning tree is. It's going to look something like this. Now suppose I want to go from here to here. Does my shortest path spanning tree starting from this thing help me? Okay, not necessarily. It would help me if the shortest path from Chicago to Poughkeepsie went through Stony Brook. Okay, then in fact the shortest way from Chicago to Poughkeepsie would be the path that goes kabunk. But in fact the shortest path might not go through there. And so if you want to find the shortest path from between any pair of vertices, okay, you need to in some sense compute it with it being an origin at some point. Okay? Any questions about that? So one shortest path out problem that comes up a lot is the problem of finding the matrix of all pairs' shortest paths. Okay? So now suppose I have n cities. Okay? Has anybody ever seen a table, like in, let's say, like a driving map, where they list n cities in the, that are important cities, and they tell you the driving distance between every pair of cities? How many people have seen a map like that and know what I'm talking about? How many people don't know what I'm talking about? A bunch of people. Good. Okay? Suppose, well, I mean, good means I now have a need to explain it again. Okay? Let's imagine a world where there were 4 cities that we care about. A, B, and C. Okay, let's think of, actually part of it is maybe you guys haven't seen printed maps anymore. How many people here has never seen a printed map? Okay, no, people have seen that. Okay? So, what I'd like to tell you is that there are times when we are interested in the all pairs, what we will call the all pairs shortest path matrix. Okay, let's take a look at this graph. Suppose we had these 4 cities. Does everybody agree that there is kind of a matrix we can build? A, B, C, D, A, B, C, D, which will give you the driving distance between every pair of cities. Does everybody see that? What's the cost of driving from A to B? According to our all-pair shortest path matrix, that is 2, right? From A to C is 5, right? A to D was 1. What's the cost from going from A to A? 0, right? So along the main diagonal, maybe we're not going to put down anything, right? What's the cost of going from B to C? What's the shortest path there? In this case, it looks like it happens to be 3, right? From B to D, what's the shortest path? It looks like there's something of weight 1, right? From C to D, what's the shortest path? This is 4, that is also 4. Okay? This is what I mean by the all pairs shortest path matrix. For every pair of vertices in the graph, we want to build if we have n vertices in the graph, we want to build an n by n table encoding all the distances between, the shortest path distance between every pair of points. Okay? Any questions about that? We agree to complete the matrix. These should be zeros. What should these values be? Okay? Yeah?
If they were 2A, then they would be the same value.
If it was an undirected graph, then it's going to be mirror symmetry. The cost of going from A to D is the same as going from D to A, right? And so we would do this would be a mirror thing. Okay, if it was a directed graph, the cost of getting from here to Poughkeepsie might be different than getting from Poughkeepsie to here. Okay? But the all-pairs shortest path matrix is this thing. Okay? Any questions about it? Okay? Has anybody, how many people have seen one of these kind of matrices before, showing the distances between everything? Okay? Who has not? You still have not? Okay, well, you weren't paying attention when I drew it then, because now you have. But why would, okay, now you've seen it, I respect that, okay? Why might one be interested in these all-pair shortest path matrices? Okay, can anybody think of a reason? Okay, yes?
Real-time lookup, or to search how long it would take to get there?
So real-time lookup, maybe Google wants some one of these things, right? Before they go and tell you what the shortest path is, they may want to tell you how far it is, right? Or if they know that they're going to be asking people again and again and again what the shortest path is, maybe you'd like to build up a table of this if you're Google. Does Google, do we think Google might be doing this for its MapQuest thing? Okay, who thinks that Google might build a lookup table? You say yes. Who thinks Google doesn't build a lookup table? I got more. Well, I have 50-50. Why don't you think Google does it this way? Okay? Yes?
because it may edit its maps if they're incorrect.
So one idea would be Google doesn't pre-build this, you're saying, because they want to adjust for it every time there is a delay someplace. Maybe, but I don't believe that. Okay, yeah? Because it's too big. How much, well, is it too, let's think about it. How big is this table going to be? N squared. And what did we say N was?
300 million.
N was 300 million. 300 million squared is too big for Google. Okay, even. Okay? So I don't believe Google pre-computes this table. Although for certain things it does pay to pre-compute a table of distances. Okay? I don't think MapQuest is one of them. Any other reasons why we might care about all pairs shortest path that anyone can think of? Okay? Yeah?
So to do the Dijkstra algorithm, so we need the shortest value of the previous path, and then we can update the other vertices, and then we can connect.
Okay, not sure I'm following that thing. What is it that Dijkstra's algorithm gives you in this matrix conceptually? Let's think about it. When you run, yeah?
So the sum of a row is a span tree?
So what was that?
The sum of a row is like a span tree?
So you're saying that the sum of a row, what is a sum of a row? Okay? A row here is going to be the distance from A to every other vertex, right? That's what a row on this matrix is. Do people agree with that? How many people agree with that? How many people don't agree with it? If you don't agree with it, I didn't explain it well. Okay, any questions? Okay, so this is going to tell me the shortest path from A to every other vertex. What algorithm do we have that gives that information? Okay, the shortest path, what? Dijkstra's algorithm. What Dijkstra's algorithm is really doing is giving you one row of this matrix. Okay, does everybody get that idea? And sometimes the claim is you might be interested in all of these things. Okay? Any questions about that? Why might you be interested in this? Well, one question might be if you want to figure out where to plant a store. Okay? Let's say that these are, let's say that you're trying to figure out where to plant a facility. What is the best place to put a store? Yeah? Right in the middle. Why do we want to put a store in the middle?
Conveniency?
What?
Conveniency, shortest distance.
Well, it depends what we're actually trying to do here. Let's think about it, okay? If we are trying to put a store, we agree that people are going to take the shortest path distance wherever they go. Is that right? If these are where our customers live, okay, it's kind of interesting for us to find a location where we minimize the distance to our customers, right? And knowing what the distance is between every point and every other point is kind of important for that. Okay? I think I'm going to leave a step out here. But there's a kind of belief that if you're trying to figure out where to locate a facility, it's important to know where everything is from every other thing. Any other questions? How many people buy that to some extent? Okay? Any questions? So there are there's reasons that often come up when you're given a graph. When you want to draw a picture of a graph, okay, it turns out that having this kind of a matrix is a useful thing. Okay? Any questions about that? Okay? So I want to ask you now, how can we compute the all pairs shortest path matrix? Okay? Yeah? One idea is to call Dijkstra's algorithm from each vertex. Does everybody see that? If I call it from vertex A, I fill in all of these elements. That cost me how much?
And I do n squared.
Let's say I was doing it for the dense graph, n squared, right? So if I was going to fill up this matrix using Dijkstra's algorithm, how much time would it take? N cubed. N times n squared, which is n cubed. Does everybody see that? Okay? Any questions? I am now going to show you an algorithm for doing it, which is not any faster than that. Okay? But which is amazing. nonetheless, okay? And it is amazing because of how simple it is once you understand it. To convince you it's simple, I'm going to show you the code. This is the all pairs shortest path algorithm I'm now going to teach you. Okay, it has 3 do loops. You've always liked do loops, right? And it has one crummy line of computation in it. Okay? And this is an algorithm called Floyd's algorithm. And I want us to try to go through how this thing works for all pairs shortest path. Because it's going to be, first of all, it's an amazing algorithm if you stop and think about it. Okay? And second, it's going to be a good lead into the subject we're going to cover, not next, but after that, which is dynamic programming. Okay? Any questions about that? So this is what the payoff is going to be, is understanding this silly little short algorithm. Okay? But any questions about what problem we're trying to solve now? If you don't understand the problem, then it's hopeless. We are trying to compute the matrix, the n by n matrix, encoding how far apart vertex I is from vertex j for all pairs, right? In fact, sort of, isn't it something a little bit like that square problem? That square problem you were asking me about that's on the homework. That's telling you in some sense for every pair of vertices whether there's a path of length 2 between them, right? So there's kind of connections a little bit between this and that, okay? I don't want to overplay that, okay? Any questions about it? So the goal is, input is a graph of length with n vertices, output is an n by n matrix telling you the distance between every pair of vertices. Any questions about that? Okay. So what we're going to do is, this is a warm-up a little bit for the dynamic programming. So just to file it away. In a dynamic programming algorithm, which we're going to talk about later, but I'm just going to mumble it for a few minutes, we're going to start by basically coming up with a recursive algorithm. Okay? An algorithm that depends upon calling itself for smaller values, okay, to solve it. And we're going to evaluate this recurrence while storing the results. That's really what's going to end up happening. Okay? And once we do this, the claim is, okay, if we do this by storing the results properly with the right recurrence, it can lead to an efficient algorithm. So let me try to just go. I have a couple of false starts here, which I'm going to try not to cover this time. Okay? And let's just go to the heart of the algorithm. I'm going to come up with a recursive description of the shortest path distance between 2 vertices. And it's going to depend upon the following definition. So let's look at this definition carefully. Okay, and ups boop. I want to get this red. It's such an interesting, green even. Okay? Suppose we have a graph where the vertices are numbered from 1 to n. That's usually the case, right? If we have if you had an adjacency matrix, it's natural to give each vertex a distinct name from 1 to n. Let's let dij superscript k be the shortest path from I to j that goes through only as intermediate vertices. Vertices 1 through k. Okay? Let's understand what this category is. I and j are vertices. We want to find what's the shortest path from I to j. We are not going to do it all at once. We're instead going to say, we're first going to compute what is the shortest path from I to j going through no other vertex as an intermediary. Then the shortest path from I to j where we're allowed to use vertex numbered 1 as an intermediary. Then vertex number 2 as an intermediary. Then vertex number 3. We're gradually in each round going to increase the size of the set of vertices that we're allowed to use as intermediaries. Okay? And in general, dij of superscript k is the shortest path from I to j where vertices 1 through k are possible intermediaries. Okay? Any questions about that? Let's maybe draw an example. Let's start with drawing an example here. Suppose, let's make a new graph here. Actually, let's say we've got here vertices 1 through 4. 1, 2, 3, 4. Okay? Let's say that the path from here is ka-chunk. Ka-chunk. Let's say that there is a path like this. Okay? Let's say there's something that goes like this. And all other edges here, let's say that this is of weight 3, this is of weight 2. What is the shortest path from 1 to, let's say, let's make this here. Wait, okay, let's say 1, 1, okay? What is the shortest path from 1 to 3, okay? Let's make this larger, I'm afraid. Let's make this really much larger. What is the shortest path from 1, vertex 1, to 3, where nothing is allowed to be used as an intermediary? What is the shortest path? Yeah?
4.
4. Does everybody agree with that? What is the shortest path where, from 1 to 3, where vertex 1 is allowed to be used as an intermediary? Still 4. It doesn't change, right? What is the shortest path from 1 to 3 using up to vertex 1 and 2 as possible intermediaries? Okay, there's a way to go from here. Let's say this was of weight 2, just to make it nicer. Okay? Does everybody see that when I allow you to use vertices 1 and 2 as possible intermediaries, there is a shorter way to get to 3 from 1? Does everybody see that? What if I am allowing you vertices 1, so if I allow you the distance, this is bad. The distance from 1 to 3, using 0 as an intermediary was 4. Using 1 as an intermediary was 4. Using up to 2 as an intermediary was 3. Using up to 3 as an intermediary was?
Still 3.
Was still 3. It's too bad. Using up to 4 as an intermediary was?
Still 3.
Fortunately, this was in fact 2.5.
Okay.
Okay, does everybody see that? You guys didn't see that the first time. Okay, now when we're allowed to use 2 as an intermediary, there was a way of getting here in 3.5. Does everybody see that? 3.5. Now there is a way of getting there in 3. Does everybody see that as I allow a richer set of intermediate vertices as a possibility, my shortest path distance is going to go down, right? Okay? And by the time I allow you to use everything as an intermediary, where this thing is the same as n, then I have given you the absolute shortest path from I to j. Okay? Does this make sense? This, at this point, I want to see make sense. It should be clear that as I allow you more vertices as possible choices for intermediaries, the distance from I to j can only get shorter, right? If they build another road someplace between here and Chicago, it is possible my distance to Chicago will get shorter, right, by going through that little hick town that road passes through. Or it might not get shorter, but it can't get longer because I give myself another option. Okay? And it should be clear that when I'm allowed to use all possibilities as intermediaries, then I have the shortest path overall. Any questions about that? That said, what is the distance, right, again, if we take a look at this thing, Bij superscript k is the shortest path from I to j using only vertices 1 through k as possible intermediaries. The initialization condition, the distance from j to j of length 0, what's the distance from j to j using 0 as an intermediary? What is that distance going to be? Okay, distance from a vertex j to vertex j using 0, using nothing as a possible intermediary. What's that distance going to be? 0, right? To get from where I am, cost me nothing, right? In general, the distance from I to j, if I is not equal to j, okay, where I'm not allowed to use any intermediate edges, is going to be the weight of any edge from I to j. If there is an edge from I to j, I'm not allowed to use an intermediary. The shortest path using no intermediary is that edge. If there is no edge between them, what is the distance from I to j of using 0 intermediaries?
Positive infinity.
Infinity. There's no path. The cheapest path is infinitely expensive. Any questions? Now, let's look at this recurrence relation, okay, and see if this makes sense. Clear ink. I claim that in general, the distance from I to j using vertices 1 through k as intermediaries is either going to go through vertex k or it is not going to go through vertex k. Does this make sense? Let's look at the two possibilities. The shortest path from vertex I to j either will go through vertex k or it won't. Okay? If it doesn't go through vertex k, my claim is the distance from I to j, where I'm allowed to go through vertex k, okay, could be the distance from I to j, where I don't go through vertex k, right? That's one possibility. If you allow me to go from here to Chicago through San Francisco, okay, I'll say thanks, but there's a shorter path that does not involve San Francisco. Right? The alternative is, I do go through vertex k. In which case, what do I want to do? I will want to go from I to vertex k, and then from vertex k to j. Does everybody see that if I'm allowed to use only the vertices less than or equal to k as intermediaries, the shortest path from I to j is either going to not use vertex k at all, or it is going to go through k, in which case the cost of that path is the cost of going to k plus the cost of going from k to my destination. Okay? Think about this. How many people see this? Okay? Think about it. It's not really that hard. It's kind of an amazing thing. But it is very straightforward. Either the shortest path goes through my last degree of freedom, or it doesn't. If it does, okay, then I pay the cost of going to k plus the cost of going from k. If it doesn't, I don't go through it. The cheapest way to get from I to k is either going to be the cost going through k or not going through k. So if I take the minimum of those possibilities, that gives me the way to do it. How many people see this? Okay? Any questions about it? Does everybody see that if I knew, okay, what, could look up in a table what dij k minus 1 is, and what dik k minus 1 is, and what dkj k minus 1 is, how much time is it going to take to fill in this number? Okay? If all these d's here are things I'm looking up in a table, how much time does it take to execute this whole statement? Okay? Constant. Why is it? It's constant time table lookup plus constant times table lookup plus constant times table lookup plus a min of two numbers. Okay? It takes constant time to update dij of superscript k if we have these intermediate values. Okay? Any questions about that? Yes? Is this k here the same as that k? Wait, which k are we talking about? This k over here is the same as this k, is the same as this k. Okay? Because this is important to see. If we have a path that's going through our new choice k, we are explicitly driving the path through it by saying I have to get from I to k and I have to get from k to j. Right? Either I'm allowed to use my last degree of freedom, I'm going to use my last degree of freedom, or I'm not. Okay? Any questions? And what's cool is, if I do this right, I know what the value of this is for k equals 0. You told me that for k equals 0, it was going to just be the adjacency matrix, the weights of the edges. I can then use it to compute for d of 1, given the values for d superscript 0. Once I have the values for d superscript 0, I can compute d superscript 2, then d superscript 3. In general, there are n cubed possible values here. This starting vertex is 1 of n, this ending vertex is 1 of n, and this superscript is 1 of n. So n times n times n is n cubed. There are n cubed of these things, okay? Each one of these things I claim I can compute in constant time once I have the other smaller things, okay? And that's going to be why I'm going to get an n cubed algorithm here. N cubed things I'm computing, each of which takes constant time. Any questions about that? Okay. Let's go back. Kabunk. What was my code? Here is my code. Clear ink. Okay. Again, my outer loop is going to be k, the intermediate vertices. For all pairs of vertices, I'm going to want to compute the shortest path from I to j using 1 through k as intermediates, using this formula. I start for k equals 0, then k equals 1, 2, 3. Okay? In general, I have 3 loops, each of which goes from 1 to n, and inside is constant time. Okay? This is an n cubed algorithm for all pairs shortest paths. Any questions about it? Okay? This is a little bit subtle, and I want you to take a look at it. Okay? Because when we go and talk about dynamic programming, people are going to get very confused. If you understand this algorithm, before we start talking about dynamic programming, you will be way ahead of the game. Any questions about shortest paths, one way or another, about anything else? Okay, if I don't get 5 minutes of questions, I'm going to go back to minimum spanning tree, so you should try to ask me some questions.
What exactly is the dynamic programming aspect of the...
What is dynamic programming? So we'll talk about dynamic programming. My definition of what dynamic programming is efficiently computing a recursive thing by storing partial results. So let's look at this. Why is this dynamic programming? Where is there a recursive thing? Do you see a recursive thing? Okay, you may say it's not recursive. I don't see any subroutine being called. But there is a recursive thing. What is the recursive thing? Yeah?
It's calling the distance k minus 1.
I'm calling this distance thing to compute it. I'm calling it in terms of smaller things, right? That is the recursive thingy. Okay? What is, I say, efficiently computing a recursive thingy? It's by storing partial results. What are the partial results that I stored? Okay? Note that if I stored a matrix for this, dijk, right? If I have to compute this every time I need it, I'm in trouble, right? But if I have an array, an n-cubed array, once I have computed this for a small value of k, originally k equals 0, then k equals 1, 2, 3. If I store it, this recurrence relation can now be evaluated in constant time. Does everybody see this? This is a recursive thingy. But the only reason this can be computed in constant time is because this is sitting in a table, and this is sitting in a table, and this is sitting in a table. Okay? And that is going to be that's what dynamic programming is. Efficiently computing a recurrence using partial results. Any questions about that? Any other questions about shortest paths? Okay? Or graph algorithms, about anything at all about graph algorithms? Still got...
Talk about these network flows.
Okay, so this is just saying, talking about network flows. I will tell you that there are a bunch of other algorithms. Again, graph algorithms is a world where there are, I will say 24 problems in graph algorithms that come up over and over and over again. What I would recommend you do during a quiet time before your Google interview is to go to the back of my book. And if you go to the back of my book, there's that big section that we're not actually going through, which is a reference guide to all the problems on algorithms, okay, that I think are important, that come up a lot, okay? One of them a couple of them I'm not talking about in here, but I think you should look at the pictures and get familiar with them. One of them is something called network flow, and it has to do with how much stuff, if you view the graph as a network of pipes, okay, you could imagine that each edge was a pipe and the weight was a capacity, how much stuff could flow through it, how much sewage could flow through it. And you start trying to pour sewage in one vertex of the graph, and you have a drain somewhere else in the other vertex of the graph. How much stuff could you flow through this graph without a pipe exploding? Okay? That is the network flow problem. It turns out it's kind of funny. You may say, I don't want to route pipes. I don't want to route sewage. But it turns out that a lot of other graph problems depend upon it. Just like I tell you that shortest path is important because it comes up as a lot of special case kind of problems of it. There are more macho problems like network flow, where even more things are sort of special cases of it. Okay, we're not going to go through it. This is where I'm going to end my graph algorithms. But I do encourage you to go and figure out what the names of these problems are. Because a lot of the problems that you will encounter in your Google interview or in your life or in any optimization thing are basically these simple standard graph problems. Okay? And learning to think in terms of what the names of these problems are and how you map to them is a large part of the battle. Any questions? That said, get beating on the homework. And next class, we're going to start to talk about a different subject, which is exhaustive search. And I look forward to talking to you guys then.